So what we're going to do now is come up with a procedure that'll let us find an equilibrium in this market. And remember, this is a market with network effects. So the equilibrium we're looking for is an equilibrium fraction using the product or the service. It's complicated because of the fact that what anyone's willing to pay for this product depends on their guess about who else is using the product. So this is a fairly complicated concept. We're looking for an equilibrium really in expectations, with the idea being that people have an expectation about the fraction of the population, the thing we call Z, using the product. And in equilibrium, we want that guess to be correct. Okay? Let's first think about why we want that to be our equilibrium concept. It's in some sense a self-fulfilling expectations equilibrium concept. We want expectations that when they operate through the market, cause the expectations themselves to be correct. And the basic idea is, look, if the expectations people have are not correct, then someone who's either buying the product or not buying the product is unhappy with their decision. They're going to want to change. If people were too optimistic, they guess too many people would buy the product, and they're going to see that actually not that many people buy the product. And that means that someone who bought it is unhappy that they bought it and would rather not have bought it. We're looking for an equilibrium situation in which everybody's making a decision that actually is the correct decision, with expectations that are actually fulfilled. So let's think about what that means in the context of the model we've been writing down. Remember, R of X is person X's reservation price without the network effect. That gets multiplied by F of Z, where Z is the fraction using the product to pick up the network effect. So person X's reservation price, if they expect fraction Z to use the product, is F of Z times R of X. What's an equilibrium going to look like? Well, it's got to be the case that in equilibrium, the people who are actually buying the product add up to fraction Z. Let's think about the last person buying the product, and since the person who's just barely willing to buy the product. That would be a person whose reservation price is exactly equal to the price in the market for the product, the thing that we've called P. That means that in an equilibrium, if people guess fraction Z are using the product, and person X is the last person using the product, F of Z times R of X would have to be equal to P. And that person X, let's figure out who that person really is. Well, if the guess Z was correct, that person X has to be person Z, have to be the same. Because remember, everyone whose name is to the left of X is buying the product, if X is the critical person there. Everyone to the right's not buying it. So what's the fraction buying the product when people guess fraction Z? It's this guy X, right at the critical point. But if it's an equilibrium, then X has to be equal to Z. And that actually gives us the procedure to use to find the equilibrium fraction Z using the product. It's just a fraction Z using the product that solves F of Z times R of Z equals P. So all we've done is plug Z into R in place of X, because we know in equilibrium, if you guess Z, Z has to be the critical person buying the product. Let's take that intuition now about what an equilibrium has to be and return to our example to actually figure out how to compute one. So in our example, remember, we had R of X equal to 1 minus X and F of Z equal to 4 times Z. And we did P equal to a half, but that's not relevant quite yet. Let's first figure out what F of Z times R of Z looks like. That in this example is going to be 4Z times 1 minus Z. Remember, we're plugging Z into R with the idea being that the critical person using the product has to be person Z if expectations Z are correct. So let's graph 4Z times 1 minus Z. That's a nice non-monotonic function. It's a little hill, pictured here in blue. It hits the Z-axis at 0 and 1, because that's what happens to F of Z for F of 0 equal to 0, and what happens to R, that is R of 1 is equal to 0, and otherwise it's a hill. In fact, this hill has a maximum at Z equal to a half, but that too isn't really relevant. What counts is that it's a hill. Okay. How do we find an equilibrium? Well, we take our price P of a half, and we just find all the points where that cuts F of Z times R of Z. And if you notice here in the picture, that price of a half drawn at this red line cuts the curve twice. It cuts it at Z prime and at Z double prime. What's that mean? Well, it means that in this market, there are actually two equilibria, both at the low expectation of Z prime and at the much higher one of Z double prime. Last time when we were doing that iteration over guesses, we were trying to find Z double prime. We weren't finding Z prime because we didn't make guesses that were low. Had we made low guesses, we would have converged to Z prime. So it looks like in this market, for this particular example, with P of a half, we actually have two equilibria that we can pick out there, a low one Z prime with a small fraction using the product and a high one Z double prime. Remember again what this means. It means that if people expect a small fraction of the population to use the product, that is Z prime, then that's actually what's going to happen in equilibrium. And if they expect a large fraction, Z double prime, to use the product, that's what's going to happen in equilibrium. That's really the critical aspect of this. How many people use the product depends on what people expect to happen. There are two self-fulfilling expectations equilibria here in which people are actually using the product. And it's also important to remember that there's another one. There's another equilibrium where everyone expects no one to use the product, that is Z equal to 0. That one's actually easy. We don't need all the math to find that. If everyone thinks that no one's going to use the product, then no one wants to buy it, and therefore no one uses it. That's always going to be an equilibrium. So this market has three equilibria: no one using the product, a small fraction Z prime using it, and a big fraction Z double prime using it. The zero case is the special one. We found Z prime and Z double prime by solving for Z times the quantity 1 minus Z equal to a half. Okay? It's important to remember that we did this for a particular price P equal to half. As you move that price around, the equilibria are going to change. An interesting case is to notice what happens if you move the price P up high enough. Right? Well, if you move it above the top of the hill, then it doesn't cut the blue curve at all, and the only equilibrium is going to be at Z equal to 0. So at a very high price, no one uses the product. As the price comes down, the point where P hits the blue curve first is just at one point right at the top of the hill. That actually occurs at P equal to 1. And then as the price comes down further, you get two equilibria that have people using the product. One in which the fraction using it is large and higher as you move the price lower. And another one in which the fraction using the product is small and gets smaller and smaller as the price comes down. So you typically have three equilibria: 0, the Z prime, and the Z double prime. What we'll do next time is take this analysis we've done and begin to use it to analyze what happens in the market for products like this.